Well, hello there. We should take a look at some of these graphs in your chapter showing the pressure waves emanating from a speaker cone. So these are longitudinal waves leaving a speaker, and of course we have to use a transverse graph to represent those pressure oscillations. So this one is supposed to tell us that the phase of the wave at t equals 0 is 0 radians. How can we tell? Well, it's really the phase shift I'm talking about. I guess we can tell because in the following, we're going to use a sine function to describe the wave. And you can scoot a sine function right or left with the phase shift, but this particular sine function has not been scooted right or left, so its phase shift would be 0. That's why they're telling us that phi sub 0, that means the phase shift at t equals 0, is 0 radians. Now, what's this about the speaker cone moving backward and a quarter cycle ago, the speaker cone was all the way forward? I think it's a little easier to visualize this stuff if we string some pictures together. So let's put a speaker cone at the origin. This is being driven by a function generator, and it's producing a sine wave tone, so a very pure tone, like a tuning fork. Okay, so this is a snapshot graph where freezing time, evidently a bunch of sinusoidal pressure oscillations have already been emanated or been emitted by the speaker. Currently, and let's think of this as the pressure wave. Currently, the pressure wave is it the pressure wave or the displacement wave? I'm going to call it the pressure wave, even though I may be wrong. And I've shown you with this black arc here that the speaker cone is currently, or the speaker membrane is currently pushed forward. It's in the forward position, and I'm just assuming that corresponds to max pressure there. It could actually be max displacement. I'm going to go with pressure. So the fact that there's a peak at the origin, this is going to be the origin here. The fact that there's a peak there matches the fact that the speaker cone is currently pushed forward. Okay, a moment later, to be specific, 1/4 period later, the speaker cone is now flat and it's about to move backwards. So the fact that the height of this sine curve here is 0 matches the fact that the speaker cone or membrane is neither forward nor backward. Another 1/4 period later, now the speaker membrane is in its furthest back position, and that's why the function has its lowest value. So the height of the curve at any time at the origin matches the position of the speaker membrane. And let me just cycle through these so you get a little mental animation. So as the speaker membrane oscillates back and forth, let's do that one more time. The wave continues to move forward. Here I go. Speaker cone is oscillating sinusoidally and producing sinusoidal waves. Okay. In the following, it will be helpful to have these numbers in the forefront of your mind, really just a couple of these. You need to know that the sine of 0 is 0. So in a moment, the slides that we're looking at have an argument for the sine function consisting of kx minus omega t plus the phase shift. That argument that we've been talking about for at least a week now. But here we're just going to call that whole thing x, just like you did in pre-calculus back in high school. So if the phase, aka argument, if the phase of sine is 0, then the height of the curve is 0. If the phase of the sine function is pi over 2, in other words, if the argument is pi over 2, then the function has its maximum value of 1. So you just want to memorize that the peak of the sine function corresponds to a phase of pi over 2. Then at a phase of pi radians, we're back down to 0. So both a phase of 0 and a phase of pi correspond to a function value of 0. See how the function has a height of 0 at both 0 radians and pi radians and 2 pi radians? So that could confuse you or mislead you into thinking that as far as phase is concerned, 0 is the same as pi, is the same as 2 pi, is the same as 3 pi. That's really not true. There is a difference because when you're at a phase of 0, the function is currently increasing as you go to the right, But at a phase of pi, the function is decreasing, opposite behaviors. Now, when you get to a phase of 2 pi, the function is increasing again. So it is fair to say that a phase of 0 is equivalent to a phase of 2 pi. And a phase of negative pi is equivalent to a phase of pi. So I'll emphasize this once more. Just because two phases produce a curve height that's the same does not mean that they're equivalent. Look at pi over 4, for instance, and 3 pi over 4. The height of the curve here and here is the same. That does not mean that the two phases are equivalent. As a rule, any phase you're talking about is equivalent to a phase that's 2 pi radians to the right or 2 pi radians to the left, which would be off the screen here. Okay, so we return to our sinusoidal progressive wave function. This is a wave traveling to the right. I know that because there's a minus sign. So wave number, angular frequency, phase shift. And in this picture, the phase shift tells you something about what the speaker was doing at t equals 0 when you started counting, or when you started the clock. So here I've set up a coordinate system. The x-axis points to the right, and let's place the origin at the front of the speaker. And this snapshot graph tells you what's happening at t equals 0. So when this crest was emitted, well, that would have been several seconds ago at least, right? This one was emitted before this one, which was emitted before this one, because the whole thing is traveling to the right. So this crest right here is currently being emitted from the speaker at this time. Now, if we'd like to evaluate the displacement at this particular place, right in front of the speaker, at this particular time, meaning the time at which the picture is happening, then we can plug in x equals 0 because the speaker's at the origin, and we can plug in t equals 0. And then we're only left with the sign of the phase shift. Now we know from looking at the picture that the wave currently being emitted has its peak right now. Again, I'm not sure if this would be the displacement or a pressure wave. Let's go with pressure. Maybe the pressure is at its maximum because the speaker is currently pushing forward. You know, you probably figured this out while I was talking. I think it's displacement. Yeah. Don't the particles right next to the speaker membrane have to experience the same displacement as the speaker membrane? So let's call this the displacement peak. It's happening right now. And that means that the phase of the sine function must be pi over 2, right? Because we already reviewed the graph of sine, and we know that it peaks at pi over 2, or pi over 2 plus 2 pi radians, or pi over 2 minus 2 pi radians. Those are all equivalent. Let's go with the easiest one. What about this one? It's obviously different because the peak has moved forward. Again, we're evaluating, and the idea here is this is a different scenario because we're still calling this t equals 0. The speaker is still at the origin. This speaker was a different speaker. It was doing something different at t equals 0. It looks like it's already emitted its maximum displacement. So this would be when the membrane of the speaker is flat. So it hasn't yet moved backwards, but it's already finished with its forward motion. We're still at the origin, so we plug in x equals 0. This is still supposed to be t equals 0, so you plug that in. You're left with this. Okay, well, what must the phase be? We know from looking at the graph of the sine function that the left side of a hump corresponds to a phase of 0, or 2 pi, or 4 pi, or you could go backwards and say it's negative 2 pi, negative 4 pi. Those all work. They're all equivalent. Remember, the sine function goes forever in both directions, so there's really no preferred starting point. Now you might be thinking, how come we can't call it a phase of pi since the sine of pi is also 0? I'm looking at the function here, and the height of the function here at the speaker, meaning at the origin, is 0. Sine of pi is also 0, so how come it's not pi? Well, you can think about it this way. The wave is moving to the right, correct? So if you imagine off to the left, the wave that's coming, that's on its way, looks like this. So a moment later, won't the height of the curve right here be actually lower? whatever the sine curve is doing over here, this scoopy upward scoop is going to scoot to the right. So the height of the curve here will actually go down in a moment. And let's just represent that, shift your frame of reference over here and look at what this particle would do. Yeah, let me draw your attention to the function here. So we just evaluated the height of the curve at x equals 0 and t equals 0. Well, what happens when you let time advance? Since it's negative omega t, as t takes on more and more positive values, you're plugging in a more and more negative number, which means you're actually going backwards on the sine curve. So if you started out, let me back up. You started out at this height. I'm really talking about the front of the speaker here. If at this moment the height of the curve is here, then as time goes on and you plug in a more negative number, then you're actually moving this direction on the sine function. And that's moving away from zero radians for your phase. If you plugged in pi radians for your phase, or your phase constant, then as time goes onwards, you would be backing up from that, keep messing this up. You'd be backing up from this position, which means you'd actually be going up. You'd be climbing one of those humps, and the function would be going higher. That doesn't work because by my prior reasoning, we know that as this wave moves towards the right from t equals 0, this point on the curve will actually dive downwards. So it has to be a phase of 0 radians, not pi. Or you could say 2 pi, not 3 pi. Or 4 pi, not 5 pi. If you don't follow that argument, just look at the picture here. Right now at t equals 0, when we're starting the clock, right in front of the speaker cone at the origin, the phase is, we're on the left side of one of the humps. That's 0 radians, not pi radians. Okay. Just to help you remember, pi, 2 pi. So what's the rule? The odd multiples of pi, that's pi, 3 pi, 5 pi, those are on the right side of a hump. See that? All the odd multiples are the right side of a hump, and the even multiples, 2 pi, 4 pi, those are on the left side of a hump. So what's this one doing? Well, this is t equals 0. And we're at the origin. Plug in 0 and 0. We already did this one, right? Okay. Moving on. So it doesn't matter if you say 0 or 2 pi or 4 pi. It's all the same. And your book doesn't really emphasize that point. Okay. Now, when we look at these pictures in the book, no problemo, man. They make sense because we've strung together some pictures and we can imagine the speaker cone moving forward and backward. Why is the phase here pi over 2? Well, because it's at the peak of a sine function, and that has to be a phase of pi over 2. Or pi over 2 plus 2 pi. Or pi over 2 plus 4 pi. Okay, what am I doing here? Once again, just emphasizing it's not enough to find two places where the height of the curve is the same. So this point is at the same height as this point, but that does not mean that this phase is equal to this phase. They're not. So every point in this green region has a unique phase, but pick an arbitrary point within that region. If you add 2 pi radians, you get an equivalent phase. It's not enough to just go from here to here. Yes, the height of the curve is the same, but those two phases are not equivalent because here you're climbing the sine function, here you're you're climbing the hump, and here you're descending the hump. So those are not equivalent phases. Ooh, what's going on here? 2 speakers. See, this is just like the picture in your book, but mine is new and improved because it's got an actual graphic of a speaker. Now, the way you really ought to think about this is these 2 speakers are almost right next to each other, so their sound waves are overlapping. Yes, the picture only shows a blue curve that's limited to a region of space, but the idea is both of these speakers are sending out longitudinal waves that are spread out over a greater region of space. So these 2 waves really are overlapped, and somebody hanging out over here would hear the sound waves from both of them. And we're interested in understanding the interference between these waves because it turns out that depending on the distance between the speakers and the relative phase between them, the sound heard by a person over here may be louder or softer. Scooting one of the speakers forward or backward would actually make the sound volume change due to this phenomenon we're investigating called interference. Interference, superposition, same thing. Okay, this is one particular position in space, but we can label it with two different coordinates. We can first describe how far this point is from speaker 1. That's the coordinate x1, but also how far it is from speaker 2. That's the coordinate x2. And we can use the familiar displacement function to describe the displacement due to each wave right here. So the displacement anywhere in this region to the right of the speakers, the displacement from speaker 1 is going to depend on how far that particular position in space is from speaker 1, also what time are we evaluating the displacement, and also what's the phase shift. So basically, what was speaker 1 doing at t equals 0? Was it in the forward position, the backward position, halfway in between? And notice we've got, let me back up, we've got some extra subscripts here. Instead of just calling this phi or phi sub 0, we're saying phi 1, 0. So it's the 0 means phase shift, what it was doing at time 0. It's the phase constant for speaker 1. So this doesn't mean 10 and 20. It's speaker 1's initial phase, speaker 2's initial phase. Let's use the symbol delta x, obviously, for the displacement between the speakers, the distance between them. I guess it would have a plus or minus, depending on which one was in front. And then delta phi sub 0 is the difference in the phase constants. So there's a couple ways you could word this here. Remember, each of these is the phase constant or phase shift for the respective speaker. We're looking at the difference between those respective phase constants. So this is the difference in the phase constants. It's also called the inherent phase difference. That's a really important term for this chapter and the next couple chapters. It tells you whether these speaker cones are wiggling together or in opposite motion or something in between. So do they push forward at the same time and backwards at the same time? Are they vibing together, or are they doing something different from each other? If they're doing the same thing, pushing forward and backward together, then the inherent phase difference would be 0 or 2 pi or 4 pi. That's something you should memorize. If the inherent phase difference is 0, 2 pi, 4 pi, 6 pi, or negative 2 pi, negative 4 pi, then it means these two are wobbling to and fro together. They're pushing forward, pushing backwards together. They're in sync. They're in phase. And you can tell from the picture that the inherent phase difference between these two speakers is not 0, because one is pushed forward and the other one is flat. Sorry, I didn't actually draw the arc for the curvature of the speaker membrane there, but you can see the curves don't match up. Well, when I say they don't match up, I mean this one currently is in its middle position. This one currently is pushed forward. That's why the height of the curve is at its maximum there. Okay. Let's also use this term, the path length difference. Really important term when we get to the double slit experiment. We talk about how to measure the wavelength of light. We need to know this phrase, the path length difference. And it really just means how much farther does this speaker's wave have to travel to get to this position, right? Speaker 2 only has to send a wave out this far. Speaker 1 has to send a wave a little bit further. Speaker 1's wave has to go a little farther from the source to get to the place we're examining. And the extra distance is called the path length difference. Now, a lot of the time, the sources that we're talking about are in phase. They're pushing forward, pushing backward together. They're in sync, as these two are. So let me distinguish between two important observations here. This wave crest is not lined up with this wave crest. So even though the crests are not aligned, and that's really due to the path length difference, their inherent phase shift is 0. So in time, the speakers are lining up. They're oscillating in phase in time, but that doesn't mean that their peaks line up in space. And the reason for that is because the two sources are in different positions. There's a path length difference between them. So you can have two oscillators synchronized in time and not be synchronized in space if there's a path length difference. It really depends on what the path length difference is. Okay, let's look at a simulation. Here's a simulation perfectly suited to our purposes, which was shared to me by a former student. So if you ever run across a really good one that you haven't seen me present, please forward it to me. We've got two sinusoidal traveling waves, and this time they're going in the same direction. Previously, we looked at progressive waves of equal amplitude, equal wave number, and equal frequency traveling in opposite directions. And we showed mathematically that the net result of that superposition is a standing wave. This time, the two waves are traveling in the same direction, and they occupy the same space. So think of it as a one-dimensional interference between progressive waves, same direction, same amplitude, same wave number, same frequency. What do you get? You get this blue curve on the bottom. And the first thing to note before I hit play is the height of the blue curve appears to be double the height of the green and the red curves. And that is not a coincidence. That's because they are in phase. See how the peaks of the green curve line up with the peaks of the red curve? Okay, so as they travel together, occupying the same space, all you have to do is take the algebraic sum of f of xt and g of xt, as they're calling it, to get the total wave. Now what happens if I introduce a phase difference? This is coming up in a future slide. So far I've just talked about the difference in their phase constants, but there's an overall phase difference that's going to depend not only on their inherent phase shift, but also on delta x, the path length difference. Now you're going to see here as I scoot this, hang on, how do I scoot this thing? Step thickness. Right. As I scoot this to the right, you'll notice that the phase of the green wave at the boundary changes. Right now it looks like its phase is pi over 2 because it's at a peak. And when I move it to the right, and now the phase is different. So I've actually changed two things. There's a different path length for the two waves, and there's also a difference in phase constants. But either way, you see what's happened to the superposition of the two. The amplitude has changed. So whereas before the total amplitude was twice the amplitude of either wave individually, now not so much. In fact, it looks like if I introduce just the right phase difference between them, I get an amplitude of 0. In this case, close to 0, but it's possible to have an amplitude of 0. So terminology, again, this would be maximum constructive interference. This would be maximum destructive interference, and in fact, because the amplitude can be made 0, you could even call it perfect destructive interference. That's only possible because the amplitudes of the two waves are different. If one amplitude is greater, then there's no way for them to perfectly interfere destructively. All right. And once I hit play, what's happening here? Do I need to refresh? I don't mean take a shower. I'm talking about the web page. Okay. If I introduce a phase difference, once I hit play, see how the amplitude of the net result, the total wave, doesn't change in time? This is the behavior that you want to be familiar with. When two waves of the same amplitude, frequency, and wavelength are traveling in the same direction in a one-dimensional situation, the total wave has the same wavelength. That's kind of interesting, right? The total wave has the same wavelength as the individual waves, and also the same frequency. You can see that by just imagining you're a bug hanging out in the net wave, and you see how you would go up and down, with the same frequency as you would for either of the individual waves. What has changed is the overall phase. See how the blue wave doesn't perfectly match up with the red one? A red peak doesn't match up with the blue peak, and a blue peak also does not match up with a green peak. So the overall phase is different from, or I should say the overall phase shift is different from the two originals, and so is the amplitude. And as I move the, what they're calling step thickness, that just really means I'm changing where the green wave starts. You can see that I can make the amplitude of the total wave be anywhere between double the amplitude of the individual waves or 0. It could be any of those. So here's an intermediate case. It stays like that in time. Same thing for this one. Stays that way in time. Okay, so the takeaway is clearly the amplitude of the total wave, which tells you the degree of constructive or destructive interference, that amplitude is going to depend on the overall phase difference between the red wave and the green wave. Do the peaks match up or do they not? In this case, there's quite a bit of mismatch. See how the peaks of the red wave are almost aligned, not quite, but almost aligned with the valleys of the green wave. If we totally align them, then they interfere. Oh, I had it for a second. You saw that, right? You get perfect destructive interference, and the total wave is 0. So which of those is occurring just depends on the phase difference between the two waves. Let's now express that mathematically. And before I do that, what does this mean for the person listening to the speaker? Well, the person to the right of those speakers in the original picture, in this scenario would hear a very quiet sound, and in this scenario, they would hear a much louder sound. Sound intensity depends on the square of the amplitude. Let's talk through some examples here. Okay, in each case, in each of these slides, we'll address the inherent phase shift, but also the phase shift introduced by a path length difference. Okay, it looks to me like these two speakers in time are actually synced up. They're pushing forward, pulling backward at the same time. So you would say that the inherent phase shift between them is 0. That's what this says right here. Delta phi sub 0 is 0. The difference between their phase constants is 0. So what would be the phase constant of this one? Well, at the origin, you plug in x equals 0. When you start the clock, you plug in t equals 0, and you get the sine of phi sub 0. You can see that that phase would have to be 0 radians. So this phase constant, which tells you what speaker 1 or speaker 2 here was doing originally, that phase constant is 0 radians. This one is also 0 radians, so the difference between the phase constants is 0. 0 minus 0 is 0, so delta phi sub 0 is 0. Wow, that's a mouthful. However, the speakers are in two different locations, so there is a path length difference. If you're asking for the total wave amplitude over here at any point, well, one of the waves has to travel farther. Speaker 2's wave has to travel farther. That's the path length difference. And in this case, it's one full wavelength. And that is the reason why the peaks still line up and the valleys still line up. You can see that if you scooted speaker 1 a little farther to the right, then the peaks would not line up between the two waves, and you would get a measure of destructive interference. So it's no coincidence that a path length difference of one wavelength doesn't change the fact that the peaks and the valleys line up. So here's a really important way of thinking about it. This is the wavefront or the peak that's currently being emitted by speaker 2, right? This one just came out of speaker 2. This one just came out of speaker 1. So this crest was emitted sometime in the past. Now, how long did it take this point on the wave to travel from the speaker to there? So at this moment in time, in this snapshot graph, this point on the wave is right here. Previously, it was here. How long did it take to travel that distance? Well, that's called the period, right? It takes one period for a point on the wave to travel this far. Well, what is this far? That distance is called the wavelength. So here's a very important point that may be obvious to you, but it takes one period for a wave to travel one wavelength, or I should say a particular point on the wave. To put that another way, how long did it take this point to get from the speaker to here? 1 period. What was the bottom speaker doing during that time? Well, during 1 period, this speaker went through another full cycle. So just as this point reaches this position here, speaker 1 is in the process of making another peak. So in other words, this speaker is producing a wave that's matched up with the one that's just arriving here from the other speaker. I can't really think of a better way to put that, but this is a nice way to summarize it. It takes 1 period to travel 1 wavelength. So during the 1 period it took this wave to get from here to there, speaker 1 went through 1 full oscillation, so it's still in sync with this wave. Okay. Here's another example. Well, what's the inherent phase difference between these two speakers? They've put one of the waves as a dashed line, one as a solid line, but you can see in this snapshot graph or picture, at this time, speaker 1 is in the process or has just emitted that crest, and speaker 2 has also emitted a crest. So they're in sync in time. They're going forward and backward together in time. So there's no inherent phase difference. There is, however, a path length difference. It's equal to 1 wavelength. So really this picture is the same as the last one, but now they're actually giving us a graph of the total wave. The total amplitude is twice the amplitude of each individual wave. They're using the lowercase a for the amplitude of each wave individually. So this would be the case of maximum constructive interference. And you could say that the overall phase difference between these two is 0, or 2 pi, or 4 pi, or 6 pi. So when you say that two waves are in phase, that's shorthand for really saying that their phase difference is 0, or 2 pi, or 4 pi, etc. What about these two? Well, speaker 2 has just finished emitting a valley, while speaker 1 has just finished emitting a peak. They're obviously not in phase in time. See, right here they're saying the sources are out of phase. To be precise, you would say they're out of phase in time. Overall, they're out of phase as well, but they're in the same position. The waves are coming from the same x-coordinate, but they're out of phase in time. Now, it's pretty clear that the inherent phase difference, that's this quantity, between them is pi radians. You know, if you take the sine function and scoot it left or right by pi radians, then you've got, you replace the down humps with up humps and vice versa. We could also do it this way. What is the phase constant for speaker 2? If this is t equals 0, what's that phase constant after you plug in x equals 0 and t equals 0? Well, this would have to be pi, right? If you think about it, a top hump is right here. We're on the right side of one of those up humps. So that's called, or that is a phase of pi radians. And the phase here is 0 radians because we're on the left side of the hump. So what's the phase difference? Pi minus 0, or I should say the inherent phase difference. Pi minus 0 is pi radians. Now check this out. You could also have, if you wanted, you could call this not just pi, you could call this phase constant 3 pi if you wanted. And this one could be called not just 0, but 2 pi. Right? 2 pi works just as well as 0 pi. So what's the difference between 3 pi and 2 pi? It's also pi radians. But I'll go one further. What if you wanted to call this one not pi, but 3 pi? Because 3 pi is equivalent to pi. And this one just keeps 0. Then the phase difference would be 3 pi minus 0, which is still 3 pi. So maybe you're thinking, which is it? Is the inherent phase difference pi radians or 3 pi radians? And the answer is, it doesn't matter, either one. So when you're talking about the phase constant of an individual speaker, you can add or subtract 2 pi, 4 pi, 6 pi, it doesn't matter. And also when you're talking about the difference in phase constants, in other words, the inherent phase difference, you can also add 2 pi, subtract 2 pi, and it doesn't matter. Okay, and the book doesn't emphasize that point, probably because it's confusing. This one is different. what's the inherent phase difference? Let's call this one a phase constant of pi. Let's call this one a phase constant of 0. So there's an inherent phase difference of pi radians, and there's also a path length difference. Now we can see that speaker 1 is a full wavelength. See the right end here is one full wavelength to the right of the front of speaker 2. Now, if there's no inherent phase difference and you shift one of the speakers by one wavelength, two wavelengths, whatever, they're still going to be in phase. But in this case, they were already out of phase in time. So they started out of phase in time, and then you shift one of them by one wavelength, they're still out of phase in time. This is the case of perfect destructive interference. Okay. Identical sources. Have I introduced this term yet? Identical sources just means that they have the same phase constant. When you see this, inherent phase difference equals 0, that means identical sources. So when they say identical, they're not talking about, both of these speakers came from the same manufacturer and they have the same power rating. It has nothing to do with the physical characteristics of the speaker. It means that they're oscillating together in time. There's no inherent phase difference. Okay, but this time, speaker 1 is not a full wavelength to the right of speaker 2, but only half a wavelength. You see, if you go one hump, there is the membrane of speaker 1. Membrane. So these have an a path length difference of half a wavelength. And check it out. They're interfering destructively. You've got the peaks of 2 lined up with the valleys of 1. That's destructive interference. So despite the fact that there's no inherent phase shift, even though the speakers are going front back together in time, they're still interfering destructively because the path length difference has introduced an additional phase difference. Okay? So the contribution from the phase constants is 0. There's no difference in their synchronization in time. But because they're half a wavelength apart, we introduce a phase shift, we say, of pi radians. All right, because you're going to see this again in the slideshow, but I'll summarize right now. If the distance between the two speakers is 1 wavelength, or 2 wavelengths, or 3, that doesn't contribute any additional phase shift. But half a wavelength corresponds to a phase shift of pi radians. So if they're already oscillating together and you scoot them apart by half a wavelength, well, now they're going to be out of phase. And a word about language again. I said a moment ago that when you say two waves are in phase, you really mean the phase difference overall is 0 or 2 pi or 4 pi. When you say two waves are out of phase, usually that's shorthand for they're out of phase by pi radians or 3 pi or 5 pi. It really just means the peaks line up with the valleys. Now what's going on here? 2 contributions. Okay. So first of all, they're not oscillating together in time. See how the phase of this guy is pi over 2, and the phase of this one is 0. So the phase difference, the inherent phase difference, is pi over 2. So they're already out of sync in time. They're out of phase, so to speak, by pi over 2 radians in time. But then there's an additional contribution to their phase shift because of the path length difference. See how you have to scoot forward 1/4 hump to get from speaker 2 to speaker 1? This is not a half hump. This is a 1/4 hump. How long does it take a wave to travel a 1/4 hump? Well, that would be half a period, right? 1 hump is half a period. No. Am I doing this right? 1 hump is half a period, so a half a hump would be a 1/4 period. Whoa. Okay, so I'm talking about humps, periods, and wavelengths. Let me just repeat that in terms of humps and periods. How long does it take a wave to travel 1 hump? That's half a period. So how long would it take to travel half a hump? That would be a 1/4 of a period. Some of you will be confused by this very verbose explanation. I know I'm using a lot of words here. It's because I'm trying to add a little bit more than what's presented in your book. I hope this is the last one here. What's the inherent phase difference? Let's confirm this number. The phase constant for this one is pi, and the phase constant for this one is 0. Yes, the difference between them, the inherent phase difference is pi radians. However, they're also shifted by half a wavelength. And you can see that the effects of those two undo each other. I'm going to put it this way. There's already a phase difference of pi inherently. So in time, they're out of sync by pi radians. But they're also shifted in distance by half a wavelength, which corresponds to half a period. So you could put it this way. There's one shift of pi radians in time. That's the inherent phase shift. But there's another shift of pi radians due to the path length difference. When you put those two together, you get an overall phase shift of 2 pi radians, and that is the same as a phase difference of 0. So they're actually in phase. So it's like the inherent phase shift canceled the effect of the phase shift introduced by the path length difference, so that overall they're in phase. Okay, now let's look at this mathematically. So far what we've done is establish visually that if you line up the peaks and the valleys, in other words, they're, quote, in phase, you get an amplitude that's double the amplitude of either wave individually. And we've established that did I say peaks and valleys? If you line up the peaks of one with the peaks of the other. Now, if you do the opposite, line up the peaks of one with the valleys of the other, then you get totally destructive interference, and the total amplitude is 0. Well, we can develop now a formula that will give us all possible results, everything in between max constructive and max destructive interference. Okay, so here's one more piece of terminology. Remember, phi10, that's related to what the speaker's doing when you start the clock. That's called the phase constant, sometimes the phase shift, but the entire quantity inside the parentheses, which is often called the argument in trigonometry, now we're going to call it the total phase, or the overall phase. So you evaluate the displacement from wave 1 at a particular point in space at a particular time, and then don't forget the phase constant. That overall number is called the phase, and it really just tells you where you are on the sine wave. That's it. Are you at the peak, the valley, somewhere in the middle? That's the phase. Same thing over here. We'll call everything inside the parentheses for displacement 2, we'll call that the phase of wave 2. Okay. What's going on here? Why have I put this slide up? Right. So we would like to know, if you're listening right here, if you've got your ear here, what's the total displacement that your eardrum will experience? Well, it's one point in space, but we've got two different coordinates to describe it. Each of those coordinates is measured with respect to its speaker. We've already seen that you just add up the displacements. That's the principle of superposition. And you can imagine where this goes next, right? We would like to add two sine functions. You're going to have to whip out your book of trigonometric identities, or consult Wikipedia or MathWorld or a bunch of other websites. This is the trig identity that we're going to use. And if you had asked me a week ago if I had this memorized, I would have said no. Now it's yes, because I've been working with it, but this is a little more obscure than the other trig identity we used already. I think you'd call this an addition formula. If you'd like to add the sine of one number to the sine of another number, you can rewrite it as the product of a sine and a cosine. Now, here's a little tip. You don't need to memorize which comes first, the a or the b, because what if you got it wrong? What if instead of a minus b, you had written b minus a? Does cosine care if you change the sign of the argument? Like the cosine of 3 versus the cosine of negative 3. Cosine doesn't care. It's an even function. So you don't even need to worry about the order. And that's how you can remember that it's a plus b that goes into the sine function and a minus b that goes into the cosine function. If you had a minus b in the sine function, then the order would matter, because the sine of negative 3 is not the same as the sine of 3. Okay, let's match up our a's and b's. How about we call this entire argument, or phase, we'll call it A, and this is B. So I'm just going to apply the formula here. And it's kind of gnarly at first. What did I do with the, so this 2 is the 2 right there. But notice that each of these also has a factor of A out front. That's why you see the A. Okay, can we simplify anything? What have I done here? Well, check it out. You've got a negative omega t and a negative omega t. That's negative 2 omega t, but that 2 gets canceled by the 2 in the denominator. That's why we just have negative omega t. And, oh, bummer. I don't think I'm going to fix this. Look what I did. This should be phi 1, 0 and phi 2, 0. I'm not going to fix that slide. See, I've got the inherent, or the phase constant for wave 1, phase constant for phase 2, add them up. So each of these should really have a subscript 0. And we've got x1 over 2, x2 over 2. Both of them have a k out front, so I combined all of that. And then what have I done here? Well, phi 1, 0 minus phi 2, 0. That's the difference in the phase constants. That's what we called a moment ago delta phi sub 0. That's the inherent phase difference. And if you're thinking, wait a minute, I thought we defined delta phi naught as phi 2, 0 minus phi 1, 0. It doesn't matter because the cosine function is even. We're going to see that right now I actually have both of these reversed from their previous definitions. But it doesn't matter because cosine is an even function. Okay, there's no omega t's in here. Why is that? Well, negative omega t and then negative negative, that's actually plus. So the omega t's canceled here, and I factored out the k, and I've got an x1 minus x2. That's the delta x. Okay, what else can we do? Let's massage this equation just a bit further. And nothing's happening in PowerPoint. Oh, right, because I wanted to show you the meaning of this. Let's have a physical interpretation of this quantity. First of all, what does it mean when you add two numbers and then divide by 2? Isn't that the average, the arithmetic mean of the two numbers? If we look at the picture, x1 is the distance from speaker 1, x2 is the distance from, what did I just say? x1 is the distance to speaker 1, x2 is the distance to speaker 2. If you add those numbers up and divide by 2, you're going to get the number that's halfway between those two distances. So this quantity, which I am calling x, your book called it x average. X is just the distance from, or it's the coordinate that describes the position we're talking about. Remember I said we'd like to know the total wave amplitude at the listener's eardrum, measured from this particular point. So you're really just shifting your origin. That's it. You're just measuring position with respect to a new special origin that's halfway between the two speakers. That's all that is. And then there's no better way to describe this than just phi average. And again, I screwed up. This should really be phi 1, 0 plus phi 2, 0 divided by 2. So I'm not talking about the total phases. It's the inherent, or the phase constants that I've added up and divided by 2. Okay, that's the function we were just looking at. Let's tweak this just a bit. I've relabeled this as x. Remember, that's the position in space that we're talking about, measured from the midpoint between the speakers. And this is labeled wrong. This should say phi 1, 0, phi 2, 0. Let's just call that whole thing phi average. It's the average phase constant. And now let's recall the fact that the wave number can be expressed in terms of the wave length. K is the reciprocal of lambda with the 2 pi in there. So I just made that substitution in here for K. And then I think we need to switch the order here. I'd like to put the cosine function out front. Oh, maybe not yet. I haven't done that yet. It looks like what I've done here, in going from here to here, I've factored out the 1/2. Because both of these terms have a 1/2. Now we can switch the order of the cosine and the sine. And we're just about done here. There's not much math left. Okay, what I've highlighted in red is something that should look very familiar. Kx minus omega t plus some constant. That is a progressive wave. That's the math function that describes a sinusoidal progressive wave traveling to the right. So we know, or we've kind of explained now mathematically, what we saw in the simulation. Two traveling waves in the same direction produce a third net wave that's also traveling to the right. And that's what we've shown. However, the amplitude may be different, and that's what this number out front is. Previously, we had a times sine of kx minus omega t. Now we've got the sine function times a more complicated expression, but all of this garbage is still just some number that you can call the amplitude. Do we need to go back to the simulation one more time? No, I think we've looked at that enough. You can go back if you'd like. Let's say a few things about how the amplitude depends on a couple things. Okay, now this time I got it right. All I did was borrow one of the intermediate steps from a couple slides ago. Remember, I massaged the equation a couple times to get it into this final form. Well, this quantity right here really is the overall phase. Phi 0 is the phase constant for wave 1. Phi 1 is a symbol that represents the overall phase. It's the number that you plug in to the progressive wave function for wave 1 after you've evaluated the position and the time. Okay, so see how this is the cosine function? Cosine of all this junk over 2. Here we have cosine of a bunch of junk over 2. So it may not be clear in this particular slide, but if you go back, you'll see that this quantity came from the total phase 1 minus the total phase 2. So terminology yet again. Delta phi sub 0, that's the inherent phase difference. That tells you if they're wobbling out of sync in time. If they're going front to back together in time, then delta phi 0 is 0 radians, or 2 pi, or 4 pi. And this is the contribution from the path length difference. So there's two contributions, two reasons why the waves coming out of these speakers might be out of phase or not perfectly in phase. Either they're out of phase in time, or they're shifted in space, or both. Either way, the number that you get here, when you account for both of those contributions, is called the overall phase difference. It's the difference in phase. And let me put it this way. If the peaks of one wave line up with the peaks of the other in space, then we say that the phase difference is 0, or 2 pi, or 4 pi, etc. If the peaks of one wave line up with the valleys of the other, and you get maximum destructive interference, then this overall phase difference would be pi radians, or 3 pi, or 5 pi, excuse me. Pi, 3 pi, 5 pi, an odd multiple. Okay, so this is perhaps more than anything you've seen so far in this slideshow. This is the most important equation. In subsequent chapters, when we talk about the interference between light waves and we even measure the wavelength of light, we have to be able to talk about the overall phase difference between two electromagnetic waves. First of all, is there an inherent phase difference between them? Well, later we're going to take a laser and split it into two by shooting it at a double slit. And since the two slits produce their own waves that came from the same laser, there's no inherent phase difference, so we don't have to worry about that. But the two pieces might be traveling different distances, so there will be a phase shift due to a path length difference. And you want to memorize this. I'll talk more about this in a second, but you can see what this first term tells you. It says, take the path length difference, compare it to the wavelength, and then just take that fraction of 2 pi radians. It's like one of the examples we looked at. The path length difference was a full wavelength. One speaker was one wavelength apart from the other speaker. So delta x here was just lambda. Well, what's lambda over lambda? That's 1. 1 times 2 pi is 2 pi. So the phase shift contributed by the fact that the speakers were one wavelength apart was 2 pi. But we know that a phase shift of 2 pi is the same as 0. And that's why the peaks and the valleys were still lined up with each other. Or peaks of one wave were lined up with the peaks of the other and the valleys of one wave were lined up with the valleys of the other. Okay, this is the contribution from the path length difference. This is the inherent phase difference. You have to account for both before you determine whether the overall waves are in phase or out of phase or something in between. Here's an example. What's the inherent phase difference? Well, this one has a phase constant of pi over 2. This one has a phase constant of 0. So the difference between them is pi over 2. So if you just look at their phase difference in time, you'd say they're pi over 2 radians out of phase, which is not the same as pi. Pi radians out of phase could be destructive, maximum destructive interference. These are only pi over 2 out of phase in time. But there's an additional phase difference contributed by the path length difference. So you can see how you have to scoot 1/4 wavelength, that's a half a hump, 1/4 wavelength to the right. A quarter wavelength corresponds to a quarter period. And a quarter period, well, that would be pi over 2 radians. So you've got pi over 2 radians shift in time, but an additional pi over 2 radian shift because of the path length difference. Overall, the phase difference between them is pi radians, and that's why the peaks of one line up with the valleys of the other. Let's do that in symbols. The path length difference is a quarter of a wavelength. So first you compare that to one wavelength. Well, that's kind of obvious. That's 1/4 of the wavelength. Well, a wavelength corresponds to 2 pi radians. So we're taking 1/4 of 2 pi, which is pi over 2. And then don't forget about the pi over 2 inherent phase shift, because when one speaker is all the way forward, the other one is in the middle, so they're not going back and forth together. Okay, the net or overall phase difference is pi radians. An overall phase difference of pi radians means the peaks of one are lined up with the valleys of another. Let's repeat that with a different picture. What's the inherent phase difference? And if you're at this point bashing your head on a wall because I'm repeating myself, well, that's better than you not getting it, right? The phase constant of this one looks to be pi. The phase constant of this one looks to be 0. So the difference between them, the inherent phase difference, is pi radians. But that's not the whole story, because they're also shifted apart from each other in space. And you can see that one speaker is half a wavelength to the right. Well, half a wavelength corresponds to pi radians, right? A full wavelength is 2 pi radians. So we've got a phase shift of pi inherently, but an additional phase shift of pi due to the path length difference. Pi plus pi is 2 pi. So overall, they're still in phase. You could say that the out of syncness in time is compensated for by the additional shift in space. In symbols, you compare the path length difference, which is lambda over 2, to the wavelength. Well, that's just a ratio of 1/2. You take that fraction of 2 pi. So there's a shift of pi due to their path length difference. There's an additional shift of pi due to the fact that they're inherently out of phase. One speaker cone is going backwards while the other one's going forwards. Overall, the phase difference is 2 pi. And that means that the peaks line up with the peaks, the valleys line up with the valleys. Okay, the next thing we need to look at is special cases. Let's summarize the conditions for max constructive and max destructive. They're just saying constructive and destructive. We should probably be more precise and say max constructive. That's when the peaks and the peaks line up and the valleys line up. Or max destructive interference, also known as perfect destructive interference, if the amplitudes of the two waves are the same. And this is when the peaks of one wave line up with the troughs or the valleys of the other. Okay, well, I've talked about this ad nauseum now. For constructive interference, max constructive, the overall phase difference, after you've accounted for the path length difference and the inherent phase difference, needs to be some multiple of 2 pi. It needs to be 0 or 2 pi or 4 pi, etc. And really, this should say 0, 1, 2, etc., and -1, -2. It doesn't even matter if that integer is negative. You may be wondering, what's up with the delta r? Here they've replaced delta x by delta r, and that's because in your book, this formula really came along when they were talking about wave sources that radiate in 2 dimensions or even 3 dimensions. Right now, we're just talking about one-dimensional interference. That's why we used the letter x. But later, more often, we'll be using the letter r, because it's really not often that we're talking about waves that move in 1 dimension. We'll be looking at light waves. Those definitely move in 3 dimensions. So delta r, delta x, same thing as far as we're concerned right now. For destructive interference, I've already established that the overall phase difference needs to be pi or 3 pi or 5 pi. It needs to be an odd multiple of pi. Now, here they've got a different way of stating it. I just said it's got to be an odd multiple of pi, negative pi, pi, 3 pi, 5 pi. What they're saying is it needs to be a half integer multiple of 2 pi, which is a slightly more complicated way of saying it. And the only reason they're doing that is so that you can still use this. So whether you're talking about constructive interference or destructive interference, if you use these formulas, you can plug in any integer value of m, any integer value. But these two statements together are the same as just saying it's got to be an odd multiple of pi. So this together just means it has to be negative 3 pi or negative pi or 3 pi. As an example, what if you plug in m equals 1 and we're talking about destructive interference? If the overall phase difference is 1 plus a half times 2 pi, well, 1 and a half, isn't that 3 halves? Excuse me. Yeah, 1 plus a half is 1 and a half. That's 3 halves. The 2's cancel and you're left with 3 pi. So in case this isn't obvious, let me just walk you through this. If you plug in m equals 0, you get 1/2 of 2 pi, which is pi. If you plug in m equals 1, you get 3 halves of 2 pi, which is 3 pi. If you plug in m equals 2, you get 2 plus a half. That's 5 halves times 2 pi, which is 5 pi. Right? So plug in any integer, and you're just going to get an odd multiple of pi. That's the easy way to remember it. If you want your waves to be in phase, then you need an overall phase shift of 2 pi, 4 pi, 6 pi, etc. If you want them to be totally out of phase, you need an overall phase shift of pi or 3 pi or 5 pi, etc. But you have to take into account the path length difference and any difference in what they're doing in time. This case would be destructive. All right, and just in case it hasn't sunk in yet, 1 plus a half, that's a half integer. So a half integer is a number halfway between 2 integers. 2 plus a half, etc. And those of you who study physics in more depth later, you're going to see a lot of half integers when you talk about fermions and the spin of an electron, and you talk about the theory of angular momentum. You'll see a lot of that. What's going on here? I'm just repeating the formula and repeating it again with different colors. Aha, so what if we're looking at the special case of identical sources? So I don't mean 2 speakers that were both made by Bose. We mean 2 speakers that are oscillating together in time, no inherent phase difference. Then we don't have to worry about this quantity, so I'll just cover that up. And for the simple case of identical sources, and that's usually what we're talking about anyway. Later, when we do the lab where we use a laser beam to measure the wavelength of light, we are definitely talking about identical sources because it's really 2 beams split from the same laser. So they're in phase in time. And then you can just say this. You can say that the phase shift introduced by the path length difference must be a multiple of 2 pi if you want max constructive interference. In other words, it has to be an even multiple of pi, 2 pi, 4 pi, 6 pi. If you'd like maximum destructive interference, if you want those waves to annihilate each other, so to speak, then you need an odd multiple of pi radians to be your phase shift due to the path length difference. Now, saying an odd multiple of pi, that's pi, 3 pi, 5 pi, that's the same as saying an half integer multiple of 2 pi. I really hope I haven't turned you off from any future videos. I know that was a lot of talking, but if it's burned into your brain now, you never have to go through that again. And I promise that will pay off later. I feel like I'm talking to you in the dark. This is creepy, right? Just a black screen while I continue to talk. All right, fade to black.